Hello, everyone. I am Luisa Andreis from BIAS in Berlin, and I'd like to talk to you about the joint work with Wolfgang König and Robert Patterson on large deviations for sparse random graphs. I will present you the results that we got on the Erdős-Renyi random graph, and at the end of the talk, I'll try to give you a quick overview on current and future projects on this topic in general frameworks. But we will focus in this talk on the Erdős-Renyi random graph that I guess we all know what it is. And we have n vertices, and the occurrence of an edge between two vertices is independent, and it has probability t over n for a positive t. And the scaling with respect to n gives us the sparse regime that we call sparse, since the expected number of edges is proportional to the number of vertices. This graph is known to undergo a phase transition in this parameter t, which is in terms of the emergence of a giant component, and it was proven by Erdős and Renyi that when t is less or equal than 1, then with high probability there is no giant component, in a sense that the largest component is proportional to log n, so negligible with respect to the total number of vertices. But when t is greater than 1, the largest component has a size which is proportional to n. It's precisely n times alpha t for a certain alpha t greater than 0, which is a solution of a certain fixed point equation. And the second largest component is known to be again with high probability proportional to log n. And we would like to recover this phase transition from the point of view of large deviations, in a sense that we would like to identify some quantities that satisfy large deviation principle and to study analytic properties of the rate function in order to see the phase transition from these analytic properties. And let me give you a quick overview on what we, as far as we know, are the only results on the large deviation principle for this sparse Erdős-Renyi random graph, which are results from O'Connell on large deviations for the size of the largest component and of the number of isolated vertices. Then there are results from Puchalski on the size of the giant components, in a sense that all is an LDP for all the size of components proportional to n together with their number of edges, and for the total number of connected components, and a result from Bordenave and Caputo in the framework of local weak convergence of finite graphs that gives an LDP for the connected components of the graph of a certain finite size, considering the structure of the graph itself, which is proven in the limit basically to be given by a tree. But what we would like somehow to consider are both giant macroscopic components and finite size / microscopic ones. And we decide somehow to focus only on the size of these connected components. And this is in order to have treatable spaces, but our results are purely combinatorics, and they should be possible. They should be possible to be extended also considering all the edges and the configuration of the components itself, but we will focus only on the size of the connected components. And we define first the most natural thing, that the object of the graph that we may imagine satisfying a large deviation principle, which is an empirical measure counting sizes of connected components, is what we call the microscopic empirical measure. And it is rescaling with n the number of components of a certain size. This is a measure belonging to the set of measures on natural numbers, because and any measure here, lambda, it's such that lambda k will tell us the fraction of components of size k. And there is one particular constraint, in a sense that we know that mi is considering all the connected components of our graph from isolated vertices to the giant one, to the largest one. So it has to be such that the total mass that we define as the sum over k of k lambda k, it's equal to 1, because this has to be the total number of vertices present in every components of every size rescaled by n. So this has to be equal to 1. But what we also know is that we expect, so here we are rescaling frequencies of components with n, but we know that we expect that macroscopic components, they are rare. They will appear with high probability in the supercritical regime. There is a unique giant component. So this measure cannot describe anything that relates to the macroscopic component. So we introduce a second quantity, which is the macroscopic empirical measure, and now it rescales the size of the component with respect to n instead of rescaling its frequency as here. And this is another, it belongs to another set of measures, which are measures taking integer values on the, in the interval 0, 1. And again, there is the constraint on that, considering all the total number of vertices, so the total mass being equal to 1. And we know that when n is fixed, alone, these two measures, they fully describe the system. They are enough, either mi or ma, they fully describe the system. But we expect that in the limit, they somehow decouple, they become complementary one to the other. One describing only microscopic components and the other only the large ones. So what we expect is that we have somehow to enlarge these spaces, because maybe this constraint here cannot be satisfied in the limit. So we want to allow these measures to be such that the total mass can be less or equal than 1, such that the limit of a microscopic measure can describe a fraction of vertices which is less than the total number of vertices actually. And this has to be true for both of these. And then we consider these two spaces, we endow them with the topology of convergence of integral with respect of compactly supported function. And then we already see that these two functions, so the total masses, they won't be continuous function in these topologies. And we consider the product of these two spaces, and we prove a large deviation principle for the pair of the empirical measures with speed n and with rate function, which is explicitly given, is such that it's plus infinity when the two measures are not compatible. So if the sum of the two total masses is greater than 1, and we have a form which is explicit, that it depends on the micro, and the one part depends on the microscopic measure, the other on the macroscopic, and we claim that the part that depends on the microscopic one is the one responsible for the phase transition. So this part of the rate function, which depends on a term which is of entropy form, so it's a sum of lambda k log lambda k over something, we claim that this is the key term that is giving us the phase transition. And indeed, we studied the minimization properties of this term. And we see that when t is less or equal than 1, then we can choose any c between 0 and 1. So we impose some c, and then we can always minimize this term on the set of microscopic measure with that prescribed total mass. And this is also always possible. There always exists a minimizer with that prescribed mass, and we even have this form of the minimizer, and it's related to Borel distribution, therefore to Galton-Watson processes. And this also tells us that any microscopic mass when t is less or equal than 1 is possible. The system can always organize itself with this microscopic mass, or at least this is what we expect. And when t is greater than 1, we can choose some c, which is greater than 1 over t, such that this function doesn't admit a minimizer in the set of measures with that precise mass. In the end, what we see is that there exists a sequence of minimizing sequences such that it converges to an optimal configuration, but with a total mass which is indeed the critical one, so the 1 over t, the last one for which is possible to construct such a lambda star. So this is somehow telling us that this function is minimized in this regime in some critical value. There is this critical value 1 over t, and this we expect that is telling us that not every microscopic mass is admissible. And we will expect then that the macroscopic mass, it will somehow be the complement of this 1 over t. But this is not what we know it is, because actually we know that the optimal macroscopic giant component in the Erdős-Rényi random graph is actually larger than the complement of this measure here. And this is because it's not enough to minimize part of the rate function, even if that part of the rate function is the most important in terms of the phase transition. We have to minimize fully the rate function, and this will tell us the optimal configuration of the graph. And indeed, we see that minimizing this for t less or equal than 1, we get that no macroscopic mass is optimal. And when t is greater than 1, we get that there is a macroscopic mass which is optimal, which is an alpha t, the solution of such a fixed point equation. And this is strictly greater than the critical one. So it's strictly greater than t minus 1 over t, which will be the complement of the critical microscopic mass that we saw by analyzing the microscopic term of the phase transition, so of the rate function. So this somehow tells us that the part of the rate function that is giving us the phase transition is that entropy-like term that we have. But in order to see the optimal configuration of the graph, then we have to include the additional terms, so that there is a part which is giving the phase transition, but then some additional term which is giving us the optimal configuration. And to conclude, let me tell you that we are dealing with this in the inhomogeneous random graph case. We would like to understand what this means in terms of this property of a part of the rate function to be minimized in the critical value with respect to self-organized criticality in models that are close to the Erdős-Rényi random graph, but that have some different critical behavior. And then we would like also to study coagulation processes, as I said, that relates to components, connected components of random graph, and we would like to study large deviations and phase transition for this. And with this, I conclude, and I thank you very much for your attention.